Okay, so we're going to take a look at some examples with probability. The first one's given us a situation where we have a spinner with 10 sections, says all are equally likely, and they're labeled 0 through 9. So we have a sample space, it's a set of 0 through 9, and they're giving us two different events to consider. Event A, spin results in a number greater than 5, and then B, the spin is even. So few things they're asking us to do here. Okay, what outcomes belong to each event? So this has nothing to do with probability yet. So if you want to just list the outcomes, that's perfectly fine. So we're going to use something called roster notation, where event A is the event that consists of anything greater than 5. So 6, 7, 8, and 9. Event B, the spin is even. So that would be 0, 2, 4, 6, or 8. So that's it as far as the outcomes belonging to each event. Now it says, what is the probability of each event? So again, if they're all equally likely outcomes, we can say the probability of event A has got to be equal to the number of ways the event can occur divided by the number of outcomes in the sample space. And then this could be a simplified fraction, a decimal, or a percent. So here we can go with a simplified fraction, just write this as 2/5. All right, so notation for probability of B. This time we have 5 outcomes in B out of the 10 possible outcomes, so I'll just simplify 5/10 right down to 1/2. All right, so there's the probability of A and B separately. Now it says, are A and B mutually exclusive? Or disjoint would be the same as mutually exclusive. Mutually exclusive means that the two events have no common outcomes, or that they can't happen at the same time. So here we can answer no, and we could say that the events share, well, they actually share 6 and 8 as common outcomes. So they share 6 and 8. As common outcomes. Another way you could answer that is no, because the two events could happen at the same time, right? If a 6 resulted, it would be greater than 5, and it would be even. Okay, so that's important. Knowing whether they're mutually exclusive or not is important in doing part D. Find the probability of A and B, which that's asking us to find the probability of the new event defined as A and B. Now, when you're trying to find the probability of A and B, you got to take the number of ways that satisfy A and B at the same time, which would really just be the number of outcomes they have in common. So here, they shared 6 and 8 as common outcomes, so there are 2 common outcomes divided by the 10 total outcomes. We'd say 1/5 is our final probability. All right, so probability next of A or B. So in general, the rule is probability of A plus probability of B minus probability of A and B. If we use this approach, we can say probability of A or B equals, well, probability of A, I'm going to go with things out of 10, so I have common denominators. 4/10 plus probability of B, we said would have been 5/10, minus the probability of A and B, which is 2/10. The reason we use this formula is since they have common outcomes, if we just added the probability of A plus the probability of B together, we would be including twice all of the outcomes that they have in common. So this part over here is subtracting away the common outcomes so that you only count them once. So now let's see, 4 plus 5, that would give me 9, minus 2, that would give me 7. So we should have a probability here of 7/10. Now, with a real small sample space like this, you could find the probability of A or B by actually just counting. So if we go back to the sample space, let's see, to satisfy either A or B at the same time, we would immediately take 6 through 9, so there are 4 outcomes. The 0 is the 5, the 2 is the 6th, and the 4 is the 7th outcome. So we got 7 outcomes out of the 10 that satisfy either A or B. All right, let's see what we got next. Based on a survey done at a college, 36% of students belong to a club, 15% belong to a club and play a sport, and finally 49% belong to a club or play a sport. Based on the information, what's the probability that a student selected at random plays a sport? All right, so let's do this. Let's make club event C and sport event S. Now this goes back to the same thing we were just looking at. If I take probability of C or S, that's a little bigger there. All right, so if I take a look at the probability of C or S, I should be able to apply that rule we had before on the last page, which is the general addition rule. So that says take the probability of C plus the probability of S, then subtract away the probability of C and S. Basically here, that would subtract away the students who are both in a club and play a sport. Now, this has 1, 2, 3, 4 different probabilities in the formula. As long as the problem tells us 3 of those probabilities, we can always solve for the 4th. So right here, 49% belong to a club or play a sport. That's giving me the probability of C or S. This is one of the very few formulas where if you want to, you can use percentages. I'm just going to go ahead and use the decimals. So 49%, I'll put 0.49. Let's see, what else? 36% right there belong to a club. So that's going to be the probability of a student belonging to a club, 0.36. And then right here, 15% belong to a club and play a sport. That's going to be the C and S. That's 0.15. So here, the only one they're leaving off is the probability that they play a sport. Okay, so 0.36 minus 0.15, that's happening on the same side of the equal sign. So 0.21 if I do the subtraction. We're not changing anything else. Now we can solve for our probability of S by just subtracting the 0.21. So it looks like, with a little bit of algebra here, that 0.28 or 28% is the probability that the student selected at random plays a sport. That's a pretty common formula, and it's one of them that students sometimes have a hard time figuring out when to apply. So, if you think about the phrasing of this problem, it talked about an or statement, it talked about an and statement, and it talked about at least one other individual probability. So that's a pretty good indication we're going to be using this formula for it. Okay, so several of the homework problems that you're going to be looking at involve trying to figure out some probabilities based on tables. So here we have a table that's showing us the number of students, males and females, who are taking certain numbers of credits during a summer semester. And it says, use the data to answer the questions that follow. Well, one of the things, I'm not really fond of this table not having totals. So I think what I would do is probably right off the bat, let's make some a row and a column here to do the totals. Now, if we just punch this up on the old calculator or take the time and add it up, see, if I punch this up, I'm getting 330 if we add up the male column here. If we add up the females, I'm getting 385. Punch that up on the calculator. Now, if we add those together, that's looking like it's 715. Right, so let's see, 94 plus the 118, so that should give me 212 for the 0 to 4 credits. 5 to 8, if we add these two values together, that should be 177. 78 plus 99 would be 177, and then 23 plus 27 would be 50. Now the 212, 177, yeah. I guess I looked at 78 plus 99 twice. And this would be 135 plus 141, so that would be 276. I even think I said those, pointed to those numbers, but for some reason saw the 78 and 99 twice. Anyway, mistakes happen. If you do this total table, the way that you would figure out that a mistake happened is 715 would have to be the total adding this way as well as adding this way. So if I left that 177 in there, that was going to give me something too small. I would have known something's wrong. All right, so there are 715 total students. That's just going to make it easier to answer probability questions. All right, so what is the probability that one of these students overall, meaning overall means maybe male, maybe female, but what's the probability they're taking at least 5 credits? All right, so there's a couple different ways to do this. I guess the most common one is people say, well, at least 5 credits would be any one of these. So what they do is they say, let's take the 276 students that are 5 to 8, and then let's add in the 177 students that are 9 through 12 credits, and then let's add in the 50 students. And we know that that would be over 715. So that gives me 276 plus 177 plus 50. That gives me 503 over 715. Now there is another way to do it, maybe a faster way to do it. Notice that these 212 students are really the only ones being left out, the ones taking less than 5 credits. If you did 715 minus 212, you also get 503. So that's another way of figuring that out. Now it wants to create a probability model for the male students. All right. Well, probability model, we basically need to just make a table here. Let's list the number of credits, and then list the probability. So that first 0 to 4 credits, all I'm going to do is take the number of males, that was 94, and divide that by the total number of males, which was 330. And since probabilities can be fractions, decimals, or percents, that's perfectly fine. For fractions like that, I don't really mind if you reduce or not. You know, if it comes out to be 2/4, yeah, we should reduce that. And yeah, you can see these are both even for sure, but I'm not terribly concerned with you reducing all the fractions. Okay, so the next one, we had 5 to 8 credits. And the number of males there was 135. And then 9 through 12, there were 78. And then finally for 13 plus, there was 23. And that would be a probability model. All you need is to list the possible values of your variable and assign give the assigned or the calculated probabilities. Now, if you use fractions, nice part about it is they'll automatically add up to exactly 1. If you use decimals or percents, you might get 1.01 or 101% if more things rounded up, or maybe 99% if more things rounded down. All right, last example here. We're given a probability model for a certain scratch-off lottery ticket. And part of the problem here says, how could you verify it was a probability model? Well, basically, the first thing you want to do is look at these numbers and make sure that they're all possible probabilities. Nothing bigger than 1 and no negative numbers. Then what we would do is add them up. So punch it up on your calculator, and let's see if we get a sum of 1 point, in this case 3 decimal places, 1.000, And looking at the last couple of digits, it looks like you will. So you do those two things, and that's a pretty safe bet that you got a probability model. Now, part A, what is the probability that a ticket does not result in winning money? All right, well, not result in winning money, that could be the loss of $2 in the top row or a break even. So I guess if we just did 0.675 plus 0.118, notice it's nicer here. We don't need to use fractions just because they give us the probability. They're not counting up the actual values. So that's going to give me 0.793, I believe, for my probability. So 79.3% chance about that you'll either lose or break even. You know, if we kind of apply our complement rule, and what if it said, hey, what's the probability that you win something? So probability of any kind of win. I mean, I could add this number plus this number plus this number, because those are the three different probabilities for winning different amounts. But the easiest thing to do would say, oh, that's 1 minus the 0.793. So I would know that that's 0.207. All right, so that's called the complement rule, and we can use that rule a lot. You know, if it asks us one probability and then gives us the probability of, you know, the complement, it's the 1 minus idea. All right, part B, how can we determine the expected value for this ticket from the consumer's perspective? All right, expected value is a kind of popular idea in a probability class. Expected value is found by summation sign, means just add them all up. Adding up all of the values times the probability. So what that means in this case is if we go back and look at that table, this top column here, if the player loses $2, we're going to call that a -2 for the value. So to start my expected value, it would be a -2. Now times that probability, which is listed in the table as 0.675. And then plus, we're just going to go to the next one. Now breaking even would be a value is 0, because you don't win, you don't lose. And 0 times anything is 0, so I'm going to skip that one. We can move on to the next one. If the player wins $2, the value to the player is going to be 2 times the probability of 0.110. Next row says win 5, so that's going to be a value of +5 times 0.085. And then finally we got value of 10 times a probability of 0.012. So if we punch this all up, that's going to give us our expected value for the ticket. Check me on this when you have time. Grab a calculator. Make sure I'm not hitting the wrong button here. I'm getting -0.585. Negative makes me happy because every lottery game is offered for a loss at the player's expense here. So the negative means the player's expecting to lose. So we're thinking that we expect to lose approximately 59 cents per play. The expected value would basically tell me, as a player, it would tell me my long-run expected average of buying this ticket. All right, so try the homework problems, see how they go, and get in touch with me with questions that you might have. Good luck, everybody.